I mean, it's good to start with the basics. I'm kind of a basic guy, so I'll speak on the basics. And then also, Svenny and I kind of collaborated on this information, so I'll give the talk, and Svenny can answer the questions. All right. Oh, right. Yeah, I mean, since this is kind of a teaching seminar here, if you have a question, please interrupt, particularly for like a clarifying comment, but if it's like a more extended discussion, maybe leave the question to the end. And I'll try to keep my eye out for a raised hand. Okay, yeah, so I was gonna start by talking about neutral atoms, and this is what we're using to make a magnetometer. And the very basic aspect of it is that you have a nucleus and electron orbiting around the atom. And so how the heck do we make that into a magnetometer? And here I'm just showing like one proton and one electron, and that's really how you can kind of think about things. And there's quantized energy levels, and an atom can absorb light, and so it can transition from one energy level to another one, and that's that's the main technique we use to read out information from the atom. But to measure a magnetic field, we need something else. We need a spin, and so an electron has spin. It's a spin 1/2 particle, and it's how this electron processes in a magnetic field is the mechanism or the physical principle that we're using to make a magnetic field measurement. And then things, in nature always get more complicated. Well, I jumped the gun here. So a spin 1/2 particle is either has spin up or spin down. And so then when you introduce then a nuclear spin, the electron and nuclear spin couple together, and you get some kind of what we call a hyperfine manifold that looks like this. And, for someone who's just using the magnetometer, maybe this information isn't that important, but just trying to give you a little bit of background. But the key thing is what happens when you apply a magnetic field. What happens to these energy levels as a magnetic field is applied? And as the magnetic field grows, the energy levels split. And so the splitting that we see here is called the Zeeman effect or Zeeman splitting, and this is the principle that we're using to measure a magnetic field. Okay, so what atoms are used in OPMs? And the vast majority use these 4 elements. You can definitely make an optically pumped magnetometer out of other elements, but these are the most commonly used ones, I would say. So we have helium, and we have potassium, rubidium, and cesium. And I think, so like all the, we're gonna hear about a lot, zero field surf OPMs, and almost all the ones we're gonna hear about use rubidium, but kind of the first ones that came out of the Princeton group use potassium because it does offer higher sensitivity. All right, so talking about rubidium, particularly rubidium-87, we look at the hyperfine ground state, it looks like this. Again, this is maybe more than you need to know, but we apply a magnetic field, we get this Zeeman splitting due to the Zeeman effect, and then also this transition here is what we call the hyperfine splitting, and these m = 0 states are not or minimally affected by magnetic fields, and that's often what's used to make an atomic clock. And so with the same atom, you can make a magnetometer or you can make an atomic clock. And so all the GPS satellites have rubidium-based atomic clocks based on them or on them to maintain precise time on GPS satellites. But hey, we're talking about magnetometers here. We're worried about this Zeeman splitting, and also you might notice this H bar omega L, and that L stands for Larmor precession frequency. And so this splitting corresponds to a frequency, and in rubidium-87, this particular gyromagnetic ratio that determines this frequency and its proportionality to a magnetic field is given by 2 pi times 7 hertz per nanotesla. Okay, here's the equation that one can use to calculate the behavior of an optically pumped magnetometer. P refers to the atomic polarization or the spin of the magnetometer or of the atoms and how that's processing around. And the main term that we're worried about here, how it responds to a magnetic field, is this polarization crossed with the magnetic field. And so I have this gyroscope over here to show precession. And so this is the precession of a top in the gravitational field of the Earth. And that is also the physics here is determined by a cross product term like we see over here. So when we're talking about precession, we're talking about something very, very analogous to a top precessing in a magnetic field. And these other terms have to do with pumping and a decoherence of the atomic polarization and things like that. But the key thing here, again, is this cross term. And the other thing to point out is this is sensitive to the total magnetic field. An optically pumped magnetometer will respond to all components of the magnetic field, and we have to do things to turn it into a vector measurement. And so a lot of the zero field surf OPMs we'll discuss are mechanized to measure a single component of the magnetic field or two components of the magnetic field. Okay, so let's talk about more physically a little bit, still schematically, but a little bit more physically, what an optically pumped magnetometer looks like. And here I'm specifically talking about the zero field surf magnetometer. And so here we have a vapor cell. So this is a glass cell that's been emptied out, sucked all the gas out of it. Then we put some a droplet of alkali metal in there and a buffer gas to limit the motion of the atoms. And these arrows here are representing the spins associated with each atom. And so when nothing is acting on the atoms in the vapor cell, all these spins are randomly oriented. And then we apply circularly polarized light. And that removes a lot of the random orientation and orients the spins generally along the direction of propagation, either parallel or anti-parallel. And then if a magnetic field comes along, in particular here what I'm showing is a magnetic field that's coming out of the page, then the spins start to precess around it. And if we look at this in kind of steady state, these spins would actually be a little bit more randomly oriented between two different angles. And there's this competition of the atoms getting pumped along the direction of polarization and then them starting to precess away as they feel the effect of the magnetic field. And so then there's a macroscopic polarization or a tip of the polarization of the atoms that we can measure. And so then how do we read that out? There's a number of different ways to read it out. The first magnetometer, optically pumped magnetometer from Princeton that was used to measure an MEG signal used a perpendicularly propagating linearly polarized probe beam. And so I apologize for this, but we talk about two different polarizations. We talk about atomic polarization, and we talk about the polarization of the light and how that changes as we propagate through the vapor cell. And so anyway, what happens is due to the so-called Faraday effect, a linearly polarized light beam going through the cell, its polarization will rotate depending on how much the spin component is oriented along the direction of propagation. And so looking at this rotation of polarization is one way to read out an optically pumped magnetometer. There's multiple ways to do it, so you'll see a lot of different flavors of magnetometers, but this is one way that it's done. And in this way, when you have this cross beam, you're primarily sensitive to the component of the magnetic field that's in and out of the page. If magnetic fields are oriented along the direction of the pump beam or along the probe beam, largely you will not measure those magnetic fields just due to the geometry of the laser beams going through the cell. Okay, so showing some more equations here. So the z direction is along the pump beam in this graphic here, in the schematic, and then along the x direction we have the probe beam. And so there's two different, so we can measure. Turns out you can measure either with absorption of the pump, polarization along the z direction, or with a perpendicular propagating beam, you can measure this x component. And so if we look at if we sweep a magnetic field from positive to negative around zero, and we look at how this polarization rotates, we'll get a signal that looks something like this. And so we got this right around zero field, we got this nice linear slope where we can make a magnetic field measurement. And so when we're using these zero field OPMs, we're right here on this linear slope. And this also points to the fact that we need to control how large the field is, because it kind of measures absolutely where zero magnetic field is. And if you look at the z component of the polarization along this direction, you get kind of a more symmetrically shaped waveform. And this is peaked up because this is actual data. It's not a nice simulated resonance. Okay, and so then there's another way to measure the polarization, which is by detecting the transmission of the pump light directly. And so many of the very compact surf OPMs that you buy operate in this manner, where you detect the transmission of the pump. And so if you look at how much light is coming through the atomic vapor on the pump beam, then you'll see this very much resonance that looks like this around zero field. And so then the question is, well, how do you then how do you get some nice linear slope to measure what the magnetic field is around zero? And we do this by applying a modulated magnetic field. And so in this case, again, we're modulating in and out of the page. And so we're hopping back and forth over the resonance with this sinusoidally modulated field. And then we go in and do lock-in demodulation. We take the photodiode output signal, send it into a lock-in amplifier, demodulate the signal, low pass filter it, and then we get, again, a linear slope. And one way to think about demodulation is essentially you're taking the derivative of this signal here. And so once again, we have this nice linear slope that we can use to do a sensitive measurement of the magnetic field. And so this is a video that from NIST that shows this concept, the single beam magnetometer. And so we have a glass vapor cell here filled with rubidium atoms. Each atom has the associated spin. And this is really going through what I already described, but it's nice to see it in a video format. Thank you to the NIST folks for developing this video. And so when the circular polarized light comes through, it orients the spins along the direction of propagation. And when a magnetic field comes along, it rotates the spin. And then it also changes the amount of transmission you have for the pump light that's coming through. And then I think this video shows as you turn the magnetic field on and off, it changes the angle of this spin polarization vector as the magnetic field changes in time. All right. Okay, and so, well, I guess it's my talk, so I'll talk about how my magnetometer works. So we do something a little bit different. We also use a single axis magnetometer, but we add another beam. And so there's two main transitions in rubidium. We call the D1 and D2 lines, and pumping is generally done on the 795 line. And in our case, we're going to add a second laser, a 780 laser beam, to do probing that's co-propagating with the pump beam. But again, we apply circularly polarized light, orient all the spins with the pump beam, and that's on the D1 or 795 light. And then we use 780 light that's linearly polarized, that goes through that co-propagates with the pump beam. And again, we look at Faraday rotation, so we get a very similar signal as we get with just looking at transmission of the pump beam. But in our case, we want to only look at the probe beam, and so we have an interference filter that blocks the pump and allows the probe beam to go to our analyzer. And then we have this special, what we call a wave plate, that adjusts the polarization of the light, and it makes circular polarized light for 795 and linearly polarized light for 780. And this gives some advantage to allow you to independently tune the properties of the probe beam, potentially to get a little bit more sensitivity. Okay, and once again, we apply this sinusoidally modulating field to define the sensitive axis of the magnetometer. And then, so these are some of the signals that come out of our magnetometer. And so this is the symmetric Faraday rotation signal that we get out, and this red fuzz is because we're applying this fast modulation. Ours is around 1 kilohertz. And then when we demodulate, we get this blue line, and again we get this very steep slope. And you can see that this the width of this resonance is some 10 nanotesla wide or so. And so that determines kind of the maximum magnetic field the atoms can experience to get a sensitive measurement. And so that's really shown in this plot. And one of the first key properties we got to know about trying to make imaging measurements with optically pumped magnetometers is that if you're running it what we call open loop, where there is no feedback to keep the magnetic field zero at the location of the atoms, then as you increase the magnetic field, it starts to roll off and is no longer linear. And so it's if you have an open loop magnetometer, you want to be operating in this couple of nanotesla region down here at the bottom of the graph. And so what I'm showing here is, again, a schematic from my work where we send 4 laser beams through an individual vapor cell so we can have 4 separate channels. And so each one of these red cylinders here is showing the sensitive volume of an individual channel. And so that's the intersection of where the laser beam overlaps with the atoms. And then around this vapor cell, I'm showing some coils. And so potentially one can use these coils to feed back to the magnetic field to always drive the magnetic field at the location of the atoms to 0. And that's what's called closed loop. So if you hear the term closed loop sensor, most typically it means that you're applying feedback to the magnetic field, drive it to 0, and the information for the feedback is derived from the signal of the atoms itself. So we take information out of the atoms, process it, drive it back to the signals, or drive it back to the coils, and continuously make the field 0 at the location of the atoms. What that allows you to do is allows you to have a much extended dynamic range. And then if there's applied magnetic field, then the coils will apply the opposite magnetic field. We can read out what the current is in these coils to determine what the magnetic field is. And this extends the linear range dramatically. And so in this case, they're showing going up to about 30 nanotesla. And this is a slide from Sandia and field line. Okay, so I've used this term SURF a lot. Maybe I should explain that. What it stands for is spin exchange relaxation free. And this is an effect that happens down near 0 field. And so let me first draw your attention to this graph over here. And so what we have on this axis here is the line width of the magnetic resonance. So if we go back up here, was talking about the width of this magnetic resonance. And as you might imagine, the narrower we make that resonance, the more sensitive of a magnetometer that we can build. And so it turns out that at very low magnetic field, the line width is quite narrow. So this, I should mention the x-axis here, that's the magnetic field. And then as you go to higher and higher field, the line width increases. And so that means the magnetometer, in essence, is going to be less sensitive. And so what's going on here then to make the line width narrower at 0 field? And so the basic idea is, so here we have this manifold of states, and collisions between rubidium atoms will scramble the spins and make them redistribute the spins across this ground state manifold. But when you go to 0 field and you have a high density of atoms, so the collisions are very fast, but the Larmor precession frequency is very low, then you can get this situation where when the spins collide, they will rapidly toggle between these between these manifold of states, and in some sense lock the spins together. Another aspect I should mention here is that this top manifold, you can see the energy level split in one way, and then the lower manifold, they split in the opposite way. And what that means in terms of spin precession is those two different manifolds, F equal 1 and F equal 2, precess in opposite directions. And so that means the red atoms here will precess in the opposite direction of the blue atoms. And so that's what I'm trying to indicate here. So say two green atoms come in, they collide, one turns into a red atom, meaning it flips down to the F equal 1 state and starts precessing in an opposite direction. Say one's green, it's precessing in one direction. But say then another atom comes in that's also experienced some precession. And at the end of it, after you go through all these collisions, the net effect is to have very little spin precession. So in essence, through collisions, the atomic spins lock together. And then it turns out they end up precessing at a slower rate. And that's because the F equal 2 level has more states. And so they predominantly spend more time in the F equal 2 level, and he gets some precession, but at a lower rate. Okay, and then finally, I'll mention that there's a couple of cross sections that determine these rates. And so here we have a spin exchange cross section, and then every once in a while the atoms will collide and completely scramble the spin. We call that spin destruction. And you see that this rate is about 4 orders of magnitude, 3 or 4 orders of magnitude lower. And so that means that the line width here in the low field can be 3 or 4 orders of magnitude narrower than what you have at high field. So an attempt at an explanation of the spin exchange relaxation-free regime. So kind of a technical point, but it's critical and also explains another reason why we want to be operating at zero field. Okay, so let me jump into some early work for the OPMs. The early work was all surf magnetometers. So the first demonstration was done at Princeton. And so here you can see Mika Ledbetter laying on a very large vapor cell with some very large beams intersecting perpendicularly inside that vapor cell. Very cool demonstration, and inspired a lot of us to attempt to continue to do this. And so the next demonstration was in my group in 2010, where we were able to measure, this is me laying with our first sensor up against my head. This was also a 4-channel sensor. Been doing that for a long time. And then we have the demonstration at NIST in the group of Sandia National, and this was done in 2012, and then QSpin in 2013 developed their sensors and did some good measurements then. And so now there's several emerging companies. I've listed a few of them here. I probably didn't get all the companies that are emerging in China at this point, but we have QSpin partnered up with Circa Magnetics and making some really nice systems. There's Fieldline and XMagTech. I believe these are all using zero field surf optically pumped magnetometers. But there are some other types of OPMs that have shown up more recently for use in MEG. And so one is the helium-4 OPM. And so in this system, it's still an optically pumped magnetometer, so we still have a vapor cell, and we still have laser light coming through. One of the interesting things about the helium OPM is it doesn't need to be heated. The helium is obviously a gas at room temperature, and so you just put an amount of helium in the cell. One aspect of this, though, is that the density of the helium in these discharges that make the magnetometer not quite as high as you get in a surf magnetometer, so it requires a somewhat larger vapor cell. So I believe this is about a cubic centimeter vapor cell. And another aspect of it, you need to promote the helium into a metastable state. So instead of heating the vapor cell, you apply a RF discharge that consumes about 10 milliwatts. So it's a very low power way to generate atoms in OPM. Yeah, go ahead.
In terms of sensitivity, is the helium-4 OPM, or the potential, is it more sensitive? Potentially, because it has a higher thermodynamic ratio, and Also, I think there's no spin exchange.
I believe there's still spin exchange. Can you verify that, Matthew? And
there are some spin exchanges in between the atoms in the stable state and the atoms in the fundamental state. We use sometimes and question or maybe more information.
yeah, I mean, one aspect or one way to look at this is if we look at the line width of the resonance. Typically, the line width of the surf magnetometer is narrower than the helium OPM, and so that tells you that there are collisions happening at a higher frequency in the helium OPM that decohere the spin state of the helium. And so as potential, I mean, I think surf still has the record. Surf OPM still has the record for the most sensitive measurement out of OPMs. And recently there was a paper from China that showed a helium OPM that operated down at 9 femtotesla per hertz using a multi-pass cell.
The question is, how evolved this technology is? Maybe there's still some more potential. This is something I'd like to know. If this maybe, I don't know if you can apply some surf regime to this channel. No.
I mean, helium OPMs have been developed for many decades. They've been flying in space for many decades, and I mean, it's pretty easy to make a lamp to pump a helium cell, and so the first OPMs, I think some of the first OPMs flying in space were the helium magnetometer, and they were lamp pumped helium OPMs. And then, but you can also do the same thing with alkali, make an alkali lamp, and so a lot of 50s, 60s alkali magnetometers were around as well. So I would say I'm not exactly sure when each technology was invented, but they've both been around for decades. I guess I'll also mention the helium OPM operates in a closed loop mode. It has triaxial operation but I should mention that 2 axes are more sensitive than the third. And then also mention the unshielded MEG using scalar OPMs is coming out of the Twin Leaf, SRI, and Princeton team. And so what's really cool about this is that it is unshielded. They're able to do this. I have the picture here where they did a measurement outside near a pond in Princeton, New Jersey. But they've also more recently shown some pictures and taken some great data where they're doing this in an office environment. And they've shown in their best magnetometers a sensitivity of 15 femtotesla per centimeter per root hertz while operating in the Earth's field. An interesting aspect of using a scalar OPM is that you're largely measuring the field component parallel to the ambient magnetic field. So if the ambient magnetic field is pointing in this direction, you're measuring small changes of the magnetic field parallel to that ambient magnetic field. When we're talking about Earth's magnetic field at 50 microtesla and a magnetic field from the brain being at 100 femtotesla or something like that, a perpendicular magnetic field is not going to rotate that angle of the magnetic field very much, and it's really not going to change the magnitude if you end up doing the math. So your presentation showed the math for that. So raise your hand and you can ask him about how that works. Anyway, this is truly groundbreaking work. So really excited to see that happen. So let me just spend a little bit of time talking about the physics principles behind the helium-4 OPM. And so this is not using circularly polarized light to pump the atoms. It's using linearly polarized light. And so the atomic spins align along the direction of the polarization. And so then we measure spin precession about the direction of that alignment. And so to read out two axes of the magnetic field, they applied two perpendicular magnetic field modulations at two different frequencies. And so here they're showing the different frequencies here. So we have one modulation at capital omega, one at lowercase omega. And then by measuring the frequency components at these two modulation frequencies, you're able to read out the magnetic field in these two directions by simply measuring, instead of Faraday rotation, just measuring the transmission through the vapor cell. And it turns out there's some sidebands that arise from these two frequencies. And by measuring the amplitude of these two sidebands, you can get a measure of the magnetic field along the x direction in this case. And so that allows you to get three axes. It's just the sensitivity along that third direction is about 6 times worse than the sensitivity along the other two directions. Okay, and then the magnetometer from Twin Leaf, this is a pulsed magnetometer. And so the typical zero field magnetometer has a continuous laser beam on, and we measure this angle of rotation. And in the case of the pulse magnetometer, you first apply the pulse, and then the spins get all aligned. This happens in about 1 microsecond. And then you turn that pulse off, turn the light off, the pump light off, and then you start probing. And because this is happening at the Earth's magnetic field, it's processing very rapidly at several hundred kilohertz. And so you get some very fast oscillation, and then so your signal is derived from this fast oscillation. You count this frequency, and because it's a frequency measurement, the frequency is really the quantity that we can measure most precisely, and so we're able to get a very, very sensitive measurement of the magnetic field. And so here's one of the measurements they have, and here's one of the I believe this is 8 channels here, 8 or 9 channels. Can't count. So this is showing a several magnetometer system, or it's in fact a gradiometer. And so the sensitivity of the gradiometer here is 15.7 femtotesla per centimeter per root hertz. Okay. Also wanted to get to the point of the difference between a squid and an OPM. So some of the key differences here are, one is that in a magnetometer, so in an optically pumped magnetometer, you're integrating the magnetic field over a volume, whereas in a squid, you're integrating the magnetic field over an area. And so if you're thinking about, all right, where exactly am I measuring the magnetic field, one needs to consider, how things integrate up, I guess, if you will, particularly if there's a gradient. And it also, that's one thing to think about, with the helium OPM, is that its vapor cell is somewhat bigger, and so it's integrating the magnetic field over a larger area. And then how is the sensitive axis determined? And so in the surf OPM, it's often determined by the direction of a modulated magnetic field. And so here I'm showing, say, if you apply a modulated field in the x direction, you measure the magnetic field in the x direction. And if you apply a modulated field in the y direction, you measure that magnetic field in that direction. It turns out also you can set things up so you put on a circulating magnetic field. So then with a surf OPM, you can measure 2 components of the magnetic field. And then for the squid, the sensitive axis is determined by the orientation of the loop. And so it's, you're measuring the magnetic field that's perpendicular to the area enclosed by the loop of the squid magnetometer. This is a table. I apologize, but I didn't know quite how else to represent this. But I wanted to kind of give you a comparison of all the different magnetometers here. And, if we look at the squid, typically for MEG is more sensitive than a lot of what we've seen so far in the optically pumped magnetometers. And, surf magnetometers operate for MEG somewhere in the range of 5 to say 20 femtotesla per root hertz. Helium OPMs, maybe 25 to 50 femtotesla per root hertz. And then we saw this nice result with the scalar OPM gradiometer measuring down to 15 femtotesla per centimeter per root hertz. In terms of bandwidth, the surf OPMs are relatively low, especially when they're operating open loop. When you operate them closed loop and have active feedback, you can flatten out the response to a higher frequency and get a bandwidth up to, say, 350 hertz in the field line sensors. Helium OPMs, because the relaxation rate is faster, it has a broader resonance, so it does have more of a 2 kilohertz line width. Closed loop, I guess it's what I was reading in the paper was 1.35 kilohertz. The scalar OPMs, to get the best sensitivity, they're operating around 300 samples per second. It's a pulsed measurement, right? So they're just every time a measurement is complete, they get one data point, and so it's not like a continuous measurement we get in these two other magnetometers. And then squid magnetometers, they have quite a wide bandwidth, and then they operate easily from 1 to 5 kilosamples a second. Then in terms of sensitive axes, surf OPMs easily have 2 axes. A third axis can be derived, say, from putting a second laser beam in the cell, so you can put 2 surf OPMs right next to each other to create a 3-axis magnetometer. Similarly, the helium OPM is a 3-axis magnetometer, but with the third axis, 6 times worse sensitivity. Scalar OPM, the sensitive axis, is parallel to the ambient magnetic field, and then the direction, the sensitive axis of a squid, is normal to the pickup loop. And then another aspect of these surf OPMs, the atoms themselves have to be kept very close to zero magnetic field. So you got to figure out a way to make that happen. So one is to make sure that the whole ambient field is very close, say less than 2 nanotesla. But you can also, as I described, operate this in closed loop, and that can extend the dynamic range. And so most recently in the field line OPM, they've been able to extend this dynamic range up to 150 nanotesla. So I should also mention there's dynamic range in the maximum field that the OPM can operate in. So a lot of these OPMs have cancellation coils. So if you're operating an open loop, you can apply a static field with that cancellation field that can bring the atoms down to zero magnetic field, and then measure fluctuations around 2 nanotesla, for example. So it's important to understand exactly what these specifications mean when you're looking at how a system operates. Scalar OPM operates in the Earth's field. That's great. Squids also have a very wide field over which they can operate. There have been squids that have operated unshielded, but typically the dynamic range for the feedback, at least I looked up the specification for the Megan system, and looked like plus or minus 20 nanotesla. Okay, so I wanted to go back to surf OPMs a little bit, talk about one of the systematic errors. I have a horrible looking equation here in front of you, but I'll just kind of highlight some aspects of it here. But what I want to point out to you is one of the main systematics, and again, why you want to keep things near zero field, is something that we call the cross-axis projection error and the effects of that. And so if one looks at the gain of a surf OPM, if you're just looking at say all the fields are at 0, and you apply a small perturbation field along your sensitive axis, then the gain of your OPM should look something like this, say along the x-axis here. But if you have some cross fields, so our sensitive axis here is set up to be in the x direction, but say there's a fields in the y and z direction, you have this cross term between bx times by, and that leads to a rotation of your sensitive axis. So say, for example, that if you put a field, in this case along the z-axis, you're measuring along the x-axis, and if you have this field along the z-axis, that rotates your sensitive axis. And so that means you're not measuring the magnetic field in the direction you thought you were measuring it. And so this is something that needs to be accounted for. The other aspect of this is that you can, this term over here, is that you can get an overall reduction in the gain of your magnetometer. So again, maybe you think you're measuring a particular amplitude, but you have this cross-axis field, and the gain of your magnetometer is reduced, and so your calibration is no longer correct. And then there's also phase errors. These cross-axis fields can implement phase errors, particularly when you have a magnetic field along the pump axis of the magnetometer. So these are all things that you need to be aware of and make sure that you take into account when you're doing an OPM measurements. And then also the companies developing these magnetometers are implementing ways to mitigate these effects. Okay, so just looking at this cross-axis projection area and the rotation of the sensitive axis. So say if along the pump direction, the Z direction, we apply a magnetic field, how much does that rotate the sensitive axis by? And so for our particular case, we were rotating the sensitive axis by about 2.9 degrees per nanotesla. Okay, and so how do you mitigate this cross-axis projection error, or CAPE? And the key thing is to maintain the atoms at zero field. And so one of the techniques that's been used is to just create coil systems that go around where you're making the sensitive measurement, and you use these coil systems to cancel the magnetic field. So this is a coil system we implemented in our person-sized shield. These are the biplanar coils that were first implemented in Nottingham. And then another way to do this is to make a closed-loop 3-axis sensor. And it's substantially harder, but these are starting to be developed now. And so the upside is you get a 3-axis measurement. That's great. And then you can operate it in closed loop. And then you also get fixed gain. The gain is set by the coils and not by some atomic parameters that can drift. A potential downside is there's crosstalk between the sensors. So if you have a sensor that you're applying a magnetic field inside of, that field can leak out and affect sensors nearby. But that can be mitigated. And so that can be large, and particularly if you have a good coil design that doesn't have a lot of leakage field, you can minimize the amount of crosstalk. So I'll talk about that a little bit more. But one thing I wanted to mention as well is, this is maybe kind of my own terminology, but there's a difference between what I would call interference and crosstalk. And so when I say interference, I'm referring to the leakage of the modulation field. So in the surf magnetometers, you would generally apply a magnetic field to define the sensitive axis. And if that field leaks over to another sensor, then that can sum with the field that's being applied at the other magnetometer and change your sensitive axis somewhat. This is easily ameliorated through calibration. So in our sensor that we built at Sandia, here, it's a little bit confusing, but say we have 5 of these sensors that are all next to each other, and then we're showing these 5 sensors here. You can see that these angles aren't in very nice directions, and that's really because we have these large coils that are around the 4 channels. We do get leakage between the 2 sensors, and so we're getting these interference that causes a little bit of rotation of the sensitive axes in our magnetometers. And then crosstalk is what I would say happens in a closed loop system, where you're canceling the magnetic field at the location of the atoms, and that leaks over to the adjacent sensor. And the mitigation there is to design feedback coils that minimize the crosstalk. And then also you can measure a crosstalk matrix that can, so that if you make a magnetic field in one measurement, you know how much that's affecting the neighboring sensor. And with that matrix, you can cancel out this effect, or post-processing, get rid of this effect. Okay, finally, just a couple words about, that's interesting. Reporting results. One is to make sure you normalize by the bandwidth of your sensor. Sometimes you don't see this, and some of the data reported was, if you truly want to report the sensitivity of your magnetometer at higher frequencies, you need to normalize it by the bandwidth. Surf magnetometers, like I said, are generally around 100 hertz bandwidth. Or closed loop, they go a little bit higher. But that's important. And another thing to note, say if you're measuring a gradiometer, you might hear 2 different things: a gradiometrically inferred sensitivity and a gradiometric sensitivity. And so I just give definitions of these down here. So when I report a gradiometrically inferred sensitivity, what I'm doing is I'm taking, say, channel 1 minus channel 2, dividing by root 2, and then taking the Fourier transform to give this noise here. And then if I'm reporting the gradiometer sensitivity, I'm simply going to take the difference between, say, channel 1 minus channel 2 and divide by the baseline of the gradiometer. And so our gradiometric sensitivity is reported over here. Turns out just because a 1.2 is close to 1.4, our gradiometric sensitivity and gradiometrically inferred sensitivity is about equal. All right, to conclude, OPMs are fundamentally different than the squid. Some of these points are that OPM integrates the field over a volume, not an area. The bandwidth is typically reduced compared to squids, particularly for the surf OPMs. The sensitivity of today's OPMs are reduced compared to that of a squid. This is mitigated by being closer to the head. You can have a smaller standoff distance because you don't have the cryogenic doer here. And there are prospects for making the OPM sensitivity better. The very best OPM is down at 0.16 femtotesla per root hertz. So if we can get some fraction of that in an MEG sensor, that would be quite interesting. The OPM responds to all components of the field, and we use these vectorization methods to read out the specific field components that we want. And 3-axis detection is possible. And then, systematic errors can arise from offset fields, and there's techniques to mitigate them. The surf and helium OPMs operate in a low field environment, whereas the scalar gradiometer operates in the Earth's field. So that's some of the main points I want you to take away from this talk. All right. Thank you very much for your attention.